Well, welcome to this RDWorks Learning Lab. Today we're going to just do a quick 8-month review where we are on the machine. Now, for those people that have been following the series, then I'm afraid there's not much new of interest here, except possibly in the last 2 or 3 minutes. So I don't want to bore you with all the things that have been going on the machine in the last 4 months, but for those people that just dip in and out, and the fact that it's a review might tempt some people to come in and take a little bit more interest in the series and these sorts of machines. When I did the 4-month review, I seem to remember ending on a bit of a quiet note, thinking that I might not have a lot more to learn or do, and that things would start slowing down. How wrong I was. I've managed to cram more into this last 4 months than I probably have in the last 10 years of my life. I mean, this little machine is basically a very good machine, mechanically. The tube was, I won't be too critical of the tube, but 4 letters ending in T would basically describe it. So let's pick up where we left off. The first tube that I had performed very erratically and I was losing power. It was a very poor performing tube. It was supposed to be a 50-watt tube, and in fact the length of it tells me that it was only 40 watts because it was only 800 millimeters long. So I replaced that with this lovely new tube, which is looks like a better quality tube, and it again is only 850 millimeters long. I bought it as a 50-watt tube, but in reality it's only a 40-watt tube. I've been suckered twice. I'm still running with this tube, but it's not the best performing tube ever. It's very inconsistent in its performance. As part of this refit, I manufactured my own clamps that are both adjustable up and down and in and out with a screw adjuster. Now, on the other side of the machine here, I've fitted a little box onto which I've got a milliamp meter and a temperature indicator. So when the water passes through the cooling jacket and comes back to the tank here, there's a thermometer on the end of the pipe which measures the water temperature as it comes back from the tube. And that's what this is displaying here. Underneath here we've got an ammeter. It's displaying up to 30 milliamps because that's the sort of area that you need if you're driving maybe something like an 80 or 100 watt tube. I've only got a 40 watt tube here, which technically means I should probably only be driving this particular tube at about 18 milliamps. If it's a 50 watt tube, it should be 20 milliamps. If it's a 60 watt tube, it's probably 22, 23 milliamps. But without that ammeter, you don't know how hard you're driving your tube. If you set your percentage to your power percentage to 60%, you're probably on this maximum limit. If you set it to 70, 80 or 90, you are what they call overdriving the tube, and you will greatly shorten the tube life. Now, I just mentioned the water system here. 1 or 2 things have changed since I talked about this at the last review. The first thing that we can see is that I've got a little plywood jacket that I've knocked up on the lacer that this box sits in. It sits into that level there. Underneath here I've got 2 50-watt halogen bulbs. Now, those halogen bulbs are actually not really light, they are heat. They're a source of heat to keep this tank from freezing during the cold weather. Now, the water in here is distilled water, and remember 4 months ago I was saying that I would have to keep an eye on the level. Well, I've not done anything to it since then, and if I take a sample of the water now and I feel it, it's not sticky, it's not green, it's distilled water, and it's remained absolutely in pristine condition now for 8 months. It's a sealed unit. As you can see, we've got condensation on the lid in here, but it does mean to say that I don't get any losses through condensation. It all just stays in the tank. It's a sealed system. The thermometer that's in the tank is also being used by this temperature controller here. When this temperature here drops below about 10 degrees C, the lights will switch on underneath this water tank to make sure it doesn't freeze. And at the same time as it switches the light on, it also switches the pump on and circulates the water through the tube, because the last thing I really want is for a glass tube to freeze. My temperature meter has also got a second input, which is here. And this is sensing the air temperature around this tube. So when the lid is closed, there's a little closed airspace around this tube. And to make sure that the tube doesn't freeze up this end either, as you can see, we've got two more lights here, and these lights actually heat up the inside of this area of the machine so that it doesn't go rusty with the damp, and also the heat passes up through this ceiling here, which is basically the floor of the laser tube enclosure. So what it does, it heats up the laser tube enclosure, which is the more important of the two things. So between the water temperature and the air temperature, which is being sensed, there's no way that this laser tube is going to freeze. Now you might wonder why I'm really worried about the laser tube freezing. Certainly in this part of the UK, which is a little bit north of London, but it's still on the coast. We're only 20 miles away from the sea. The weather doesn't get really cold here, not like it does up in Scotland, and maybe in some of your climates. But today is a wonderfully clear day, and tonight is going to be a really frosty night. I can tell you that now. And so consequently the temperature outside, the air temperature, even though we don't get much snow, the air temperature during the winter months can sometimes get down maybe -4, -5, sometimes as low as -10, but generally 4 or 5 is as low as it'll get during the winter. But even so, as you can see, my machine is right next to the outside world. The only thing that stops it is an insulated roller door. So I have to make sure that the machine doesn't get cold. When I first received the machine, it had got a water cutout safety valve fitted just where those two white posts are. Basically what that does, it makes sure that you can't fire the laser tube if there's no water flow. So it's a flow meter, or a flow switch, should I say. To be honest, it used to fail regularly and stop me from using the machine. So consequently what I did was to short the wires out here to make it look as though it was on and okay all the time. Now that was a dangerous practice, but I did that for a short time while I replaced the actual flow switch. It reduces the flow in this line from 2 litres a minute to about 1.9 litres a minute. So basically it hasn't had much effect on the flow, but it seems to be a much more reliable switch. One of the most interesting things that I've purchased is this power meter. Now it looks a very simple construction, and in fact it is a very simple construction. Basically it's been described to me as a meat thermometer with a block of aluminium that's been erudited to the end of it. It's easy enough to make, isn't it? Yes, I suppose so, but there's a little bit more to it than that. I'm not going to go into it now because it may well be the subject of a future video, but this has been one of the most powerful tools that I've had in helping to sort out various problems and issues that I've had with the machine. Now you'll notice since the last time I have removed the pressure gauge on here because it isn't necessary. But in addition to that, if you look carefully, you'll see that I've completely changed the way in which this head is mounted on here. I've made my own bracketry now to make sure that this head can move up and down and in and out. Now that was a necessary requirement for a simplified beam alignment technique that I have used or developed. It means you don't have to set your mirrors. The mirrors, basically, you don't touch them, you leave them alone. You just tweak them very gently, but you don't keep fiddling with your mirrors. I've had to modify my machine. I've hacksawed the corner of the machine out here and put a little door on so that I can get access to my mirror mounts, which are in here. And I've also modified the mirror mounts as well with different screws, mounting screws and spring arrangements. It was getting far too complicated and difficult to get access to these screws, to make them adjustable. These thumb screws here are no longer thumb screws, they've got a slot across them so I can adjust them with a screwdriver through this hole here. Everything has been made easier to set up and adjust, and I can change all the mirrors on this machine in about 10 minutes. What was a fearful project at one stage all of a sudden has become dead easy. The other thing that I've developed to help me set mirrors up is this little thing here. Basically it's a laser pointer. Produces a little red spot and allows me to put this at the back of the machine pointing out of the laser tube to simulate the path of the laser around these mirrors, and that makes it extremely easy to rip a mirror off, modify it, set it, do whatever I want to the mirror, put it back, and immediately within a few seconds have it completely realigned to where it was before. Now the design for this is freely available when you look at the video about it. Now the other subject that we tackled was all about the laser itself as a beam of energy. How dangerous is it? What precautions should you take? Why should you be careful of certain things? And that was covered in a subject called reflectance. Because as I have mentioned before, certain materials, like the base plate in this machine, is made of aluminium. Well, there's a piece of aluminium. Now it might not look very reflective to you, but to infrared radiation, that's like a shiny mirror. Now, that's a shiny-ish type mirror, and it makes little or no difference to the amount of reflected radiation, whether it's that side or that side. It will still reflect a huge amount of radiation. Here we've got copper. Now, look, this is totally unreflective. Again, on this side, we've got a piece that's been polished and a piece that hasn't been polished. Okay, this is marginally more reflective than this. This might be 96%, this might be 98 or 99%, but it's still very reflective as a material. Now that's very strange because infrared radiation is basically heat. This is one of the best known conductors of heat around. So when I fire infrared radiation, which is a beam of heat, at something which is an incredibly good heat conductor, you would expect this to get hot and all the energy to be absorbed in here. Totally wrong. To infrared radiation frequency, this is like a very, very shiny mirror. Now you've just seen my lights come on in the background there. That's the heating coming on for the inside of the machine. And one of the outcomes of that was an understanding of just how reflective copper is. So then I started on a quest, because with my power meter I was able to see that at the back here, when I checked the beam power coming out of the laser, I had 38 watts. But by the time it had passed through one mirror there, one mirror here, one mirror here, and a lens there, the amount of energy that was down here was actually only 30 watts. So I was losing 8 watts along this light path. Okay, it's only 8 watts. But 8 watts out of 38, that's a very high percentage loss. And so that basically set the tone for several sessions of trying to establish just why and where I was losing this power. Now it did bring up some very interesting subjects, one of which was these mirrors. There's a myth on the internet that basically says if you can get hold of a hard disk platter, which is what this is a shiny hard disk platter before I wrecked it and made a mirror out of it. This is the mirror that I made, and I substituted it for one of the mirrors that's in here and did a power test on it to see just what its transmissivity was. It's about 80–85% efficient, not very good at all. If you put 3 of these around your machine, you would lose a lot of power. So I think that's really busted that myth. Don't waste your time making mirrors out of a hard disk unless you're really, really desperate. When we came back to looking at copper and its reflectance, that made me realise that maybe there was a material there that we could use to make mirrors with, and that's copper sheet. I've made my own mirrors for this machine now. This is the second set. There's a set of mirrors in here that's working incredibly well. They're working probably better than most of the mirrors that you can buy. We can get these up to about 99.5% transmission. These are just incredibly good. They might tarnish over time, which is the reason why I've made the mirrors easily replaceable. I can whip the mirrors in and out, just give them a quick buff up and put them back in. But I'm happy to leave these mirrors that I made myself in the machine. And along with an HQ lens, which I've put in here now, I've improved this loss from 8 watts down to about 3 watts. So I've gained 4 or 5 watts of energy down here. Very small amount, and really I shouldn't be chasing that, but because I had so little to start with, it's been a worthwhile exercise to get another 15 or 20% power out of the machine. Now, one of the other things that I've discovered as well in this last session, when I tried to set the mirrors up, was that yet another reason for me losing power down at the lens is that the beam, which I previously thought should come in on the centre line, in fact, if you take it in on the centre line, it misses the mirror at the back here. It clips the edge of the mirror, and that was another reason for losing power going down to the bottom there. So this line that's here now is in fact the centre that I've got to aim for to get the beam onto the centre of the mirror. So basically I've wrung about as much performance out of this laser tube as I possibly can. Hopefully what I'm now going to do is to benefit from all this work, because I've decided I've had enough with this silly 40-watt tube. One of the problems with this tube is its inconsistent performance. Let me just turn the machine on and I'll see if we can demonstrate what I mean. Now, I've got a little test in here at the moment, a program which is going to do nothing more than run backwards and forwards and side to side. You will hardly notice the head moving, but what I really want you to do is to listen to the laser in the background. So let's start the machine off and just listen. Ah, can you hear that hiss? Sounds as though the air is running, but it's not the air running. I'll switch the air pump on now and you'll hear it. There's the air. There's no air. There's the tube running at the moment in this what they call pre-ignition mode. I've just given it what I call a little laser kiss. You haven't seen any change to the tube itself, to the light, but what's happened is it's gone past this pre-ignition stage and it's running in its proper full current carrying mode. And there we go, look, as I said, in this full power mode it will be running at about 19 milliamps, which it is. Let's turn it off and I'll try and run the program again. It may or may not start in this pre-ignition mode. No, it's gone straight up to correct operating mode now. It's inconsistent in its performance. Sometimes it will start up perfectly okay and other times it gets stuck in this pre-ignition mode. So what I've decided to do is to dump this tube and this power supply and upgrade my system to 60 watts. I've now got a peak performing machine. All I need is a good steady performing laser, and so that's the big decision that I've made. Today I've ordered myself a new 60 watt laser. Last time we spoke I was using my fairly new board design, which had got magnets in, and I was using the pogo pins which go right the way through and actually reference on the steel plate that's at the back there. So they go right through this plate. Now, as you can see, after a little while these plates get a little bit disreputable because any excess energy gets absorbed by this acrylic. It doesn't get reflected off the base plate. Not that much would be reflected off of the steel base plate, but this does a great job of absorbing any energy and you get absolutely zero reflections. I took the opportunity of using my laser to spot and make some brand new plates, and I've changed the principle slightly this time. I went out and bought, for something like about £10, I bought 100 of these very nice stainless steel 2mm dowels that are about 35mm long, and they drop right the way through the plate, and listen, you can hear them touching the steel base plate at the back there. They literally just drop through there, and that provides me with a completely flexible bed plate system. And this time, instead of magnets, what I've done, I've put some little rubber feet down to hold them in place. Now, the other thing that I can do if I really want to lock everything together, I can always call upon my little neodymium magnets that I've got here, and they really stick things down and provide me with an excellent reference which I can slide around, but they will basically lock these plates in place. That's the final design, I think, of my bed plate. I've got a fairly good stock of those 8mm plates. They were offcuts from somebody else's job, which I managed to get at an incredibly good price. almost close to free. And so I'm never going to run it a bid plate. I'm just dreaming what I'm going to be able to do with 60 watts of power. I suspect I'll be able to cut house bricks eventually, because look, with 30 watts I'm able to cut 15mm acrylic. Now that's quite incredible. It cuts it very slowly at 1mm per second, but look at the finish on it. I mean, it's a beautiful crystal clear finish. Now I think I've maxed the machine out. I don't think I can get much more performance out of the machine. It's as efficient as it can be now that I fully understand where all the problems and errors were. In the last 4 months I've learned a great deal. I've tried to impart most of what I've learned to you guys as well, and I hope that it's been a benefit to you. So we'll see what the next 4 months brings, and thanks for joining me.